Thanks. I will start. So, Heavenly Father, we thank you for this day. I thank you for the students. Pray with us, help us to just understand the material we go over today, and just to encourage the students if they're struggling, Lord. In your name I pray. Amen. All right, so here we go. So this is Calculus 3 in 30 minutes. Well, not all of it, but unfortunately, I have, well, we all want to make Calculus 3 a prerequisite for this course, but then people got to graduate on time and stuff like that. It's very annoying. So no, you can't just take every mathematical prerequisite under the sun before you take this course. So, but on the other hand, to not talk about vector calculus and the discussion of physics, in my opinion, is, well, sad. So here goes. The first idea I have to talk to you about is basically what's a function of several variables. This is not terribly complicated. I can't spell. Several variables. Yay. Okay. So you might say like this. F equals to a function of x and y, right? Or you might talk about f being a function of x, y, and z. All right. So here, x and y are independent variables, or x, y, and z are independent variables. All right. Functions of 2 or 3 variables. Here's some examples. So like, we could have f of x comma y equal to, say, x squared plus y squared, you know? Or you could have f of x, y, z equal to, say, cosine of x plus y plus e to the z squared. I mean, whatever. All your favorite functions with more letters, right? Nothing terribly surprising here. Now, if you start trying to think about how to visualize these things, well, that's harder, right? You could graph a function of 2 variables. Sure, you could do that. And you could look at z equals f of x, y, and that's what we do in Calculus 3. That doesn't really matter much to us in here. What matters to us in here is the notion of a level, really a level curve, or perhaps a level surface at some point. So what's a level curve? What's a level curve? Something like this. X squared plus y squared equals to c. The solution set to that equation is what's known as a level curve. The level function here is f of x comma y equals to what? So we're looking at f of x comma y equal to x squared plus y squared equals to a constant, right? So the level function here, you could say, is x squared plus y squared, and this is level c. Now, of course, you know what these are, right? If I change c, we get what? Circles. But you could do other stuff, right? You could do something like x squared plus y cubed plus 1 over xy equals to 42. I mean, whatever. That's still a level curve. I don't advise you try to solve for y there, right? But still, the solution set to this equation defines some curve in the plane. Okay? It's true. Don't make me graph it. So these are level curves. If you take an equation with 2 variables, x and y, right, and you have one equation, how many, like intuitively speaking, you have 1 variable left, right? Two variables, 1 equation, that means basically you're left with one free parameter. What happens then, the next order up this chain, of course, would be a level surface. So a level surface would be something like x squared plus y squared plus z squared equals to a constant, right? Now here the level function, I usually use a capital F for this one. I have f of x, y, z equal to x squared plus y squared plus z squared, right? Now what does that look like? Well, this is an equation which states that the point x, y, z, its distance squared is c, right? So if I rewrite this constant c in a more, fun way, so say that c is equal to r squared. What that is then, of course, is the equation of a sphere centered at the origin of radius r, because x squared plus y squared plus z squared, what is it? I mean, let's think about the vector stuff we already know in here, right? This is nothing more than the length of the vector x, y, z squared, right? So this is the solution set to that is the collection of all points, which are some, fixed distance r from the origin. It's a sphere of radius r. I suppose you could write this as the union of two graphs. You could solve for z on the northern half, you could solve for z on the southern half, and you could look at the sphere as the union of two graphs, but we won't do that. We don't need to do that. That's calculus 3. Level surface is where it's at. Let's see, here's another one. How about this? Another example before I get into the calculus here. How about this? ax plus by plus cz equals to d. That's a level surface. Yeah, that's a plane. And if you know it's a plane, you probably had Calc 3 before, right? But in fact, this is the equation of a plane with normal A, B, C. Now, it would take me a little work to prove that for you from analytic geometry in here, and I'd kind of rather show you why that's the normal in terms of calculus instead. So, all right. So these are the basic players in the game: level curves, level surfaces. The significance of these for us is going to be that this little f or this big F, these are going to play the role basically of potential energy for a conservative force, or next semester for the voltage function corresponding to an electric force. So these are very interesting. They have to do with the energy of conservative forces, level surfaces, and level functions. Okay, so it's going to be a little bit before I can put that all out. I'm just telling you, I'm not just talking about this because I like to talk about calculus 3, although you got me, it's true. There's a reason. All right, so partial differentiation. What on earth is partial differentiation? So I'll give you a definition. So if I have a function of two variables, all right, partial f, partial x. What this is, by definition, at the point, let's say, at the point a comma b, all right? I'm talking about function of two variables again. This will be, you take the derivative with respect to, well, I guess I could say, I'll say x. Take the derivative with respect to x, all right, of f of x comma b, all right? You do that, and after all that's done, you set x equals to a. Partial f, partial y at the point a comma b. Well, you take the derivative with respect to y of f of a comma y, and then at the very end of all that, you set y equals to b. It's immediately true then from these definitions that if I look at, for example, partial x, what do I get? Right, I get ddx of x. And then after, at the point a comma b, all right. So I take this, and then at the end I put x equals to a again. Okay, so I've got the number 1, and then I put x equals to a again. So, okay, I've got the number 1. I mean, let me not belabor the definitions. The point of these definitions, all they're telling you is to take a partial derivative, you differentiate with respect to the variable which you're differentiating, all right? And you hold the rest of them as if they were constants. That's it. That's all it is. So, with that in mind, what's partial y, partial x? Right? Partial y, partial y? Partial y, partial x, partial y, rather. 0, right? Oops, sorry.
Is that different from dy dx? Is that not?
Yes. Yeah, partial y partial x is not the same as dy dx.
What is that letter?
This?
Yeah.
Partial.
Like, is it a Greek letter?
I don't know.
Oh, okay.
I don't think so.
Like, I understood that.
It's not d. I mean, that much I can tell you.
Okay.
It's lowercase delta. Okay. What's up? Is that? Oh, okay. I think the uppercase, isn't the uppercase delta the triangle? The lowercase delta is the delta? I don't know. Yeah. You can Wolfram alpha it later. That's fine. Or Google it, whatever floats your boat. The definition for 3 variables is just the same. You just add a c and fix the other two remaining variables. Okay, so let me show you some examples. For example, over here, these guys, I'll just go back to my original examples. For this, I have, for example, partial f, partial x equals to 2x, partial f, partial y is 2y, all right? Now, we also use the notation f sub x, or this is f sub y, that's popular notation. I guess I should let you in on that. And by the way, from this, then we can do more. We can even calculate second derivatives, like partial squared f, partial x squared, or partial squared f, partial y squared, or partial squared f, partial x, partial y, or in principle, we could calculate partial squared f, partial y, partial x. And these are iterated derivatives just like in Calc 1. So what's partial squared f is what?
fxx.
Right, it's also fxx, but it's more, for my example here, it's 2, right? And this is also 2. And this is, let's see here, so partial x of what? 2y. And this is partial y of what? 2x, which is 0. That's not an accident. That's an inevitability. The mixed partial derivative, you can commute them, except for the most malevolent of examples. I have to work really hard to come up with an example where that's not true, okay? Any questions so far? How about these guys? Like here, let's see here, so we have like partial f, partial z would be minus sine, oh, I'm sorry, what am I talking about? Well, yeah, let me write it out actually. Minus sine of x plus y, but then why doesn't that matter? Partial z of what? X plus y. Right, by the chain rule. Chain rule is still true. Still true. Basically, you proceed like normal. You just have these new guiding principles, like this one, and this one, and this one, and this one. Yeah. And so in 3 variables, there are actually 9 things to think about, right? Like you have partial x is 1, partial x, partial y, 0, partial x, partial z, 0, partial y, partial x. Oh, excuse me. Yeah, partial y, partial x, 0, partial y, 1, partial y, partial z, 0, partial z, partial x, 0, partial z, partial y. Why am I writing this all out? 0, partial z, partial z. I regret this. 1. Those 9 things kind of guide us. Otherwise, we just differentiate like usual. This is a function of another function. So it's minus sine of the derivative of the inside function. But hey, I didn't even need to write this because if we are holding x and y as constants when we take a z partial derivative, this is like cosine of 7. It differentiates to nothing. as is evidenced by this because these are 0, right? So 0. And then we've got what? 2z e to the z squared by the chain rule as usual. So there you go. Partial f partial z is twice z times e to the z squared. In contrast, what would fx be in this case? And that just happens to also be fy in this case, right? All right, one more example, and then I'll go on to the theory here. Let's see here. I need another board to write on is what I need. I guess we don't need these definitions anymore. Let me get rid of them. Actually, before I do more examples, I want to introduce another player to the game. We'll do more partial differentiation, but a significant part of our thinking is in what's known as the gradient vector. Actually, it's a gradient vector field. It's actually a vector field. And what is a vector field? Well, that's a significant question in and of itself. I'll talk more about that as we go on here. But the definition of the gradient is just this. In R2, okay, the gradient of f is a vector. It's partial f partial x, comma, partial f partial y. In R3, three-dimensional physical problems, gradient of f is partial f partial x, comma, partial f, partial y, and guess what? It's third. Yeah, partial f, partial z. You got it. Now, the reason that this is a vector field is this, I wrote it, these are actually functional equations. Like, to be more pedantic about it, you have the gradient of f at the point a comma b is equal to this. It's fx at the point a comma b, fy at the point a comma b. Or if you like to be like most Calc 3 books, you might write something like this. Partial f partial x at the point a comma b, x hat, partial f partial x, partial y rather, at the point a comma b, y hat. It's the attachment. See, what you're doing is you're attaching a vector, gradient of f, at the point a comma b, and you're doing that for all points. So this isn't the assignment of a single vector, it's the assignment of a vector at each point. And that's what a vector field is. Okay. So a good example of a vector field in 3 dimensions might be the wind. You go outside, the wind is blowing, right? If you could pick any point in space, right, and you could put like a little string there, you could watch which way the string was flowing, right? And that would tell you the velocity vector of the wind. You think about those collectively, you've got a vector field, the velocity field of the wind, right? Or you could, 2-dimensionally, you could think about a stream, right? You could drop a drop of ink in there, and you could watch where it goes, right? And that would give you what's called an integral curve of a vector, of a flow line. It would be a flow line. And the flow line is matching up with the velocity field of the liquid as it's flowing. But a vector field is, again, just the attachment of a vector to each point in some object. You could talk about vector fields along a line. You could talk about vector fields along a surface. You could talk about vector fields along a curve. I mean, vector field, the idea of a vector field is very general. Excuse me. So let's see here. Let's actually investigate what's this vector field look like. So what's the deal? What's the deal with the gradient of f? What's it look like? I mean, what's its significance? Let's look at an example before I give you any proofs. We'll go back to my initial example. We'll look at the level curve, x squared plus y squared equals to, let's say, r squared, right? So if that, again, I'm going to say that my f of xy is x squared plus y squared. I just plotted, I attempted to draw the level curve, which is a circle, right? Right? Now, okay, it's a circle. What's the gradient vector field for x squared plus y squared? What's it look like? Nabla. By the way, I can tell you what this is called. This guy is called nabla. Nabla. I did not know this, and I heard a lecture by my general relativity professor, Arkady Kefitz. He was wow, that guy. He's hardcore. But he had a full blown flu. And he was like drenched with sweat, right? Like sweat is just dripping off his nose. You can see that he is running like a flu fever. It is bad. He's kind of shaking a little bit, and he's coughing like this. Like every so often, and we're like, we can take a day off. Go rest. It's okay. It's like, no, I must go on. So he's like, but one of the same lectures, he was like drawing stuff, and he's like, blah, 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 blah. I'm like, what? And I only found out later he was saying nabla, because we were talking about that. So that's where I learned of nabla. Anyway, so here you got 2x, you got 2y. Sorry, that story has very little to do with this. What does that look like? What's this vector field look like? Let me try to draw it over here for a second before I talk about the circle. A vector field, right? It's really hard to draw at the origin because it's 0 there. So there's an illustration. Now if you go out here to the circle of radius 1, what does it look like? Arrows pointing out. Let's say this point right here. Which is this point? This point would be 1, 0, right? So you feed 1, 0 into here, put x equal to 1, put y equal to 0, we get what?
2, 0.
2, 0. Up here, this point is 0, 1, right? So at this point, we get this guy. Over here, you get, well, you see what's going to happen here. Minus 2, 0 over here. Down here, you got 0, minus 2. And then the same song and dance all the way around, right? It's this totally, how many of these should you draw? I don't know. It's up to you. How many is enough? I don't know. I think I'm definitely past the point of enough at this point. What's the significance of those vectors? So it's kind of inconvenient to draw them actually the length that they are. When we draw pictures about vector fields, what I usually like to do is just draw ones that are representative of the direction. So, the same thing over here. I'm just not going to try to draw them to actually be as long as they should be, okay? So don't take anything from the magnitude of these vectors. I'm just trying to illustrate the direction, which is radially outward. Okay, that's all. What's the significance? Yeah, okay, very good. They're normal to the circle, that's true. In the sense that if you drew a tangent to the circle, right, they'd be perpendicular. Totally on board with that. How about if I think about another circle? So if this circle has radius 1 or whatever, and I look at another one out here, which has radius, say, 1.4, you see which direction the gradient vector is pointing towards? The higher level, right? The gradient vector points in the direction that you need to go to level up. So like level 1, level 1.4. So that's what the gradient vector field significance is. If you study a level curve, like this one, then the gradient vector field will point normal to it. These are supposed to be normal. And not just that, it tells you the direction you need to go off the level curve in order to do what? In order to go to the next level.
What do you mean by level?
Well, this is something like f of x comma y equals to, I guess I'm using little f, equals to some function, some stuff
Yeah.
in x and y. I don't want to be general. Don't ask me for the formula here. I don't know. Okay? But this equals to a constant. This is the level C curve for f. If you want me to be more mathematically precise, I could say it's the inverse image of the singleton C under the continuous map f. I mean, I could say something like that, but that wouldn't be helpful. So I shouldn't say it. Strike it from the record. All right. So the point is, as you change C, you get different level curves. You understand it over here for a circle. If I change the radius, I get different circles, right? Again, this will actually represent the potential energy of a physical body. And so we're interested in how the potential energy changes as you go from point to point, from level to level. It's a slight lie. There's a minus involved. All right? Well, let me just get it out. Let me just tell you now. Why not? There's no point in delaying it. A conservative force field, F conservative, means there exists some function, let's say phi, such that F is equal to minus the gradient of phi. Phi is called the potential function for the force. Sometimes I use a U. Sometimes I'll call it PE for potential energy. All right? That minus, why is there a minus there? I mean, in a math book, they call a function like f, they call it a potential function. Right? Well, that's because mathematicians don't care about conserving energy. But we do in here. Although, of course, I'm just a Mr. Cook in here. I am not a Dr. Cook. But anyway, you know, I still have some things to tell you about this. So that's going to be, a conservative vector field is one which you can capture by the gradient of some scalar function. By the way, the little f and the capital F here were scalar functions. That means their output is just a number. I'm debating whether or not I want to show you that it's normal. I'm going to show you, and then I'll behave. This may not be necessary, what I'm about to show you. It's healthy to see, though. So, if you have a level surface or curve, you can rewrite it as something like f of r equals to a constant, right? Where r is either, I'm either thinking of r being x comma y or x, y, z, right? So it's either a level curve or a level surface in my thinking, okay? Now, suppose you have a path which lies on the surface, right? So, like this, here's the surface maybe. And then I've got some path, some curve. Let's give it a name, Bob. Okay, so Bob is a curve in the surface, right? So if you take a particular point on Bob, you could say it's parametrized. You could say that's r of t, right? Maybe Bob is right there on the surface at time t. Let's let it be the position of Bob. So then, to say that Bob's on the surface is to say that f of r of t is equal to a constant for all t, for all time. All right? And then we can differentiate. All right? And here I'm just going to drop some Calc 3 on you, but when you differentiate this, there's a chain rule for a function of several variables. Well, you guys can differentiate the right-hand side, right? What's the derivative of a constant? Yeah, that's 0. That's easy. And on the other hand, what you end up with, the chain rule is, in fact, the gradient of the level function evaluated at the path. So the derivative of the outside curve is the gradient. So the gradient, some people would say the gradient is the derivative for several variables. That's a useful heuristic. So it's the gradient of the outside function, derivative of the outside function, which is the gradient of f at r of t, dotted with the derivative of the inside function. Well, the inside function is dr dt. Now you know that, you know that, you love that. That's one of your favorite test 1 questions. That's a question about, oh man, I didn't really test that, did I? I'll get back to it. This is the velocity. I mean, the calculus question I had on your test was one-dimensional. Right? I said here's a velocity in one dimension, find acceleration position. Some other years I ask a velocity that's 3-dimensional, right? That'd be more like this way of thinking. So this is the velocity vector, right? The dr dt is, you can think about that as being right here, right? So what is this? This says that the gradient, right, of f at some point dotted with the velocity vector at that same point is equal to 0. So that proves the assertion that Matthew made here a couple minutes ago. In fact, this is what the gradient vector to f looks like at the point P. It's perpendicular to the surface. This calculation also works in 2 dimensions, or 27. I mean, whatever. This is general. This comment I'm making. If you describe something as the level set of a function of several variables, if you take a path in that level set, the gradient vector to the level set will be perpendicular to the velocity vector of the path. So, and that is tied to this idea that you're leveling up, right? If you go the same, if you stay on the, if you think about it, right? If I stay on the same level, if I don't change the level, I would need to be perpendicular to the normal, right? So it must be that the normal direction is the direction in which f is changing. I haven't proved everything in here, nor should I. If you take Calculus 3 with me, I will prove these things in gory detail. Or you can watch the YouTube. I did it there last semester. Okay, so those are the toys, the main toys I want to play with. The other one, integral calculus. We still need some integral calculus. I forgot about my integral calculus. What is my problem? That's pretty much it for the differential calculus that we need. For integral calculus, I basically just need to tell you one new thing, which is the definition of the integral along a curve of a vector field. So the integral of f dot dr. So I'm defining this notation for you, and I'm going to explain its physical significance as we go. So here we have a curve. It goes from one point, let's say P, to another point, let's say Q, all right? And we've got some path that goes from P to Q. Now, I want to also suppose that I have a vector field which is reasonably well behaved close to the curve, let's say. So you could draw a picture of the vector field as it, as it's attached to the curve. Maybe it looks like this. I don't know. Doesn't have to line up with it. It could be perpendicular. It could line up with it. It could do all kinds of crazy stuff. Anyway, here's a picture of the vector field f. There's, at each point along the curve, we've attached the vector, right? I'm defining then for you, what is the definition of the integral over the curve of f dot dr? By definition, this is the integral from, say, t1 to t2 of f of r of t dotted with dr dt, where here I'm supposing that c is parametrized by r, which is a path which goes from time 1 to time 2, right? This is either r2 or r3. I mean, you could put rn here or whatever. So this is, c is parametrized by such a path. What is this? I mean, it's a definition. You're like, it's a definition. You don't have to justify why you can make it. I mean, I guess you do, right? What's the significance of this quantity is my question to you. I guess that kind of begs the question, what do you already know about physics? I don't know what you know about physics. You may or may not have ever had a course in physics, all right? So let me go back, way back to the very start of things. We introduced this thing called work, all right? And work is, in its most sort of primordial, in the educational terms form, is force times distance, right? So let me just give you a kind of a, this is your life for work. So work to start with is force times distance. For example, if I take Mr. Top Hat here and he puts a force of 10 newtons on a box and that box goes 30 meters, then the work is just equal to 10 newtons times 30 meters. Bam, you've got yourself 300 joules, because obviously a newton meter is equal to a joule, right? It's not really obvious. That's a definition. Okay. There's this guy named Joule. We want to give him credit. So there you go. Force times distance. Now this assumes, okay, that the force, this was a constant force, right? And it also assumes that the force was done in the same direction as the motion. Next hypothetical. What if instead you move the box the same distance, but with 10 newtons put at this angle, like here. Let's see here. I need to describe this geometrically. I suppose that angle is 45 degrees, all right? And again, you move the box 30 meters. How much work have you done? See, it's no longer just 10 newtons times 30 meters. Only the part of the force which is applied in the direction of the motion gives you work. So, like, only this piece is actually doing work, right? So the work done is, 10 newtons times cosine of 45 degrees times 30 meters. Whatever that is. 5 squared to 230? Well, okay, but you guys are just messing with me. Did I say 30 meters? I meant 30 times the square root of 2 meters. There, fixed. So then square root 2's cancel, and we've got ourselves, oh, that was kind of silly, because now I'm back to 300 joules. But we went further. So I was trying to draw a contrast between these examples, but my inability to pick up a calculator and punch a number has destroyed it. Hope you can forgive me. The larger point here is we could say that the work is equal to the force dot the displacement. So this is for constant force, again, is the assumption. The next level of sophistication you may have been exposed to, although hasn't happened in my calc 2, would be work done by a variable force over one dimension. Like the spring force. Right? So if I wanted to calculate the work done by a spring as it goes from, say, x equals to a, all the way out to x equals to b, what I have to do is, remember the force is equal to minus kx in this case. All right, so to get the little bit of work done, what happened?
The fan.
Oh, yeah. It's always a problem I have, my fans. But Sorry. I'm sorry. That was awful. It's just all this. Shut up. dW. What's the little bit of work done by this force over a little bitty, if I go from, say, x, right, to, say, x plus dx. In other words, I just move just a little bit. The spring moves just a little bit. How much work is done over that? Well, then I can go back to this case. At the infinitesimal level, I can say, well, it's minus kx times dx, see, because while the force changes over a finite interval over an infinitesimal interval, it's pretty much constant. So then to get the work from A to B, I integrate. And I get myself minus 1/2 kx squared evaluated from A to B. I get minus 1/2 kb squared minus, well, plus 1/2 ka squared. That would be the work done in one dimension by a variable force, which is lining up with the motion. All right? This subsumes all of these. What we're doing here in this line integral, as it's called, is we're calculating the work done by the vector field f over the curve C. This calculates the work done by the vector field f over the curve C. Now, just to try to blow up a little piece here, so you're going from, say, r, right, over to here to, say, r plus dr. So the displacement along the curve in that case is this guy, which is dr, right? So to get the little bit of dw along the curve, I've got f, right, dot dr. And I just add those up to get the net work done. Now, nobody can calculate that, so we rewrite it in terms of a parameterization. And so what we do is we just say, okay, well, I'm going to take that and I'm going to divide by dt, and I'm going to multiply by dt to be fair, because after all, I know how to write things in terms of time and add them up. You got it? Can you see it? I guess the question I should do is, questionable. I think I need some kind of like periscope apparatus here. Some kind of light bending. Yeah. Ha! There we go. So look, this definition is the natural extension of these ideas to the case where you have a force which is possibly variable over space, over a curve which is not just linear. But you can still calculate the work done by an arbitrary force over an arbitrary curve. That's pretty neat, I think. All right, so now, you know, calling this work and saying it has something to do with physics, it doesn't make a bit of sense until we do the derivation I'm about to do. Once I do the derivation I'm about to do, all of a sudden calling this thing something called work and attaching it to physical motion starts to make sense. I mean, why are you multiplying force times distance? What does this have to do with motion? It's just something I made up, and some of you agreed with me because you've seen it before, right? How does this help you find out how fast a box is sliding down a plane after it's been doing such? I mean, I haven't explained that yet. So, the first tool in our toolbox, which we must develop past to the ones we already have, is the work-energy theorem. Work-energy theorem is, oh, it's amazing. All right, so here it is. So if, all right, and this is a big if F is equal to the net force, all right, on a mass, right, then what? Newton's second law says what? Can we agree? I mean, this isn't up for debate. It's an experimentally verified fact. Okay, fine, we're stuck with this. Blame Newton if you want. Then you can calculate the work done, all right? What is the work done by such a force, such a net force? Over some path, c. And I'm going to assume the path is again parameterized over some duration of time, say time 1 to time 2. Okay, so definition then. This is, by definition, the integral from, say, t1 to t2, right, of f of r of t, right, dotted with dr dt, dt. All right. So what? Well, f is what? It's also the integral from t1 to t2 of what? Of m. Well, this is really what? This is really dv dt dot v, right? So here I'm using that the acceleration is dv dt, which we know, right? Acceleration, instantaneous acceleration is the derivative of the velocity. And the velocity, well, that's the derivative of the position vector. These things we know. Aha! Well, everybody knows that that is the same as the integral from t1 to t2 of the derivative with respect to t of 1/2 mv squared dt. I joke. Let's go through some details here. How do I get that blue arrow? What's the meaning of v without a vector squared? Remember, the magnitude of v is equal to v, right? Or if you like, squared, squared, and this is, by the way, v dot v. Remember, this is the relation between dot product and squared magnitude. Okay, we know these things. If you look at the derivative with respect to time of v dot v, what do you get? You get what? Instantaneous speed. You get the change in the instantaneous speed squared. True. Not what I was fishing for. How about this? You get this, right? But this is what? So you got acceleration dot velocity plus velocity dot acceleration. That's really just twice the velocity dot the acceleration because the dot product commutes, right? So you see, I can trade then, or in other words, I've got 2 times v, 2 times dv dt dot v is equal to, well, if I divide the 2 to the other side, right, I get 1/2. Yeah, I will eventually figure this out here. v dv is equal to what? Well, I mean, I'm being stupid. I'm sorry. What I said here is fine. It's weird how at the end of class I'm not able to think as well. I don't know why that would be. It's really strange. It's like there's some annoying, incessant white noise in here which can't be removed. I hate you. Sorry. Are we allowed to hate fans?
I think inanimate objects are okay.
We can hate inanimate objects? Okay.
I think that's fine.
I think it's slightly animated though. I don't know.
You really hate the person who put the fan there.
I should hate the person who put the fan there. Spoken like a true Trump supporter. All right, let's see here. So I'm working Trump into all my classes. As a private citizen, though. Not as an employee. Okay, so where are we? Do you see how we get from there to there now? See, because this gives us 1/2. Well, I can pull the half inside, so I have d dt of 1/2 v dot v is equal to v dot a. Just divide this by 2 and bring the half inside the derivative, you see. We have that this is equal to 1/2 d dt, but this is exactly 1/2 v squared, right? Do you see it? Well, I hope you see it. Now, we have to do some name calling. Again, as good supporters of Donald Trump, we appreciate this. Let's see here. So, we will call this kinetic energy. Not a very effective insult, but still, there it is. So, what we have then is we've got the kinetic energy at time 2 minus the kinetic energy at time 1. By what? The fundamental theorem of calculus, right? The integral, well, or an implication of it anyway. We're integrating a total derivative, so we just get the thing back out again, right? In other words, this is the change in kinetic energy. The work done is equal to the change in kinetic energy. It's the work done by the net force. I should emphasize that. That's only true for the net force. Okay? I mean, if it happens to be true for another force, it's a coincidence. At this point, you should be like, well, that's really great, but what on earth does it have to do with this? Right? Okay, glad you asked. Sort of asked. So if f is equal to minus the gradient of a scalar function phi, then we can calculate the integral along the curve of f dot dr just the same. And so that will be, I'll pull the minus out, minus the integral of the gradient of phi dot dr, assuming it's conservative. Again, this is the definition of conservative force, is that it can be written as the gradient of a scalar potential function with a minus, for reasons which are about to become clear. So then what? There's this other theorem, I guess I should fess up. The other significance of the gradient is, goodness gracious, it's a lot like, right? It's a lot like, so what this is phi of, I guess I needed names for this, I guess r of t2 minus phi of r of t1, where I'm assuming going from here to here is the so-called fundamental theorem of calculus for line integrals. You can easily prove this by just going back to here and using the chain rule I mentioned earlier and erased. It's actually because of the chain rule and the ordinary fundamental theorem of calculus you get this theorem. Again, your Calculus 3 course will give you the details here. But once you have that, oh man, that's really cool, because if I call this thing potential energy at time 2, and if I call this thing potential energy at time 1, or PE1 for short, what we then have is we have minus PE2 minus PE1, right? Which you could say is minus the change in the potential energy. In other words, the work done by conservative force minus the change in the potential energy. So what happens if the net force is conservative? Our brain explodes. No. Not that. Then you get both of these things together, And then we get the change in kinetic energy is equal to minus the change in the potential energy. But it's a lot more fun to write this as kinetic energy 1 plus potential energy 1 equals to, or 2, let's say, kinetic energy 1 plus potential energy 1. In other words, E1 is equal to E2. The total mechanical energy is conserved. What is total mechanical energy? Well, definition. E is equal to the kinetic energy plus the potential energy. That's the total mechanical energy at the moment. As you go on and study more physics, you might learn about chemical energy, or nuclear energy, or other kinds of energy, and you can add those. I am not talking about the kind of energy that Oprah talks about. That's ethereal. That's mystic. This is not mystical energy. This is not something you can sell to your friends in some sort of multi-level marketing scheme. Not the case. I'm sorry, it's a business. It's serious. There's a good reason we can't sell it at Walmart or on Amazon like every single other thing known to man. I'm sure there's a good reason for it. Or a conspiracy. Hey, did I ever tell you guys about the Walmart conspiracy? Not the Walmart, excuse me. The Walmart conspiracy. That's a different one. Do you guys know about the McDonald's conspiracy?
No.
Did you know that there's a McDonald's in North Korea? In the capital, at the heart of darkness, there's a McDonald's. There's a McDonald's. Small towns in China have McDonald's. There's a McDonald's in Brazil. There's a McDonald's in Peru. There's a McDonald's in Picuristan in Europe. They're everywhere, aren't they? Why is that? That's right. They rule the world. If you start thinking about it, McDonald's is everywhere. They probably control currency. Right, what's in the burger? We don't know. We don't know. I can't take credit for this, and that's not the complete development of the McDonald's conspiracy. That's just that's a start of it. You have to work on it for yourself to create the totality of the McDonald's conspiracy. That is merely the starting point. My brother's dream is to finish this and make a website that expounds the McDonald's conspiracy and gathers followers. This hoax will be complete only when my mother sends him an email about the conspiracy which he created. Then he will feel like his job is complete and he has done his due diligence. So, yes. Bill. There was more to it. I can't remember the proper statement of the McDonald's conspiracy, but it's fun to think about. There is no McDonald's in North Korea. Just you want to believe it because it's believable, right? It's just total nonsense, but it sounds like it could be true, doesn't it? Should probably. Who's it goes to North Korea? What? Did you say Barack?
No, I said, what did you say?
Who goes to North Korea? Who is it? Is there?
Rodman.
It's Dennis Rodman. That's right. That's right. I bet he's a Trump supporter. I don't know. Oh, he probably feels the burn. Probably. Okay, I digress. Anyway, so we have this wonderful new thing, conservation of energy. And we can solve problems with conservation of energy that are just, oh man, let me show you how it works. Let's work an example here. So the better part of the next few lectures I'll be spending using conservation of energy to solve physical problems. Here's an example of one. Inclined plane, whoop, yeep. You have a box at the top, you give it a shove. Its initial velocity is v naught. The height